Good morning or afternoon, everybody, depending on where you are, and welcome to the October Hydrography Community Call. My name is Alexander Jonasy with the National Geospatial Program's Topographic Data Services Group. Drew Decker with the User Engagement Group, who normally runs these calls, couldn't be here today. In a few moments, we'll begin today's topic, but before that, I want to see if there are any immediate announcements from our USGS 3D hydrography program leads, Steve Achel, Sue Budo, or Sylvia Terziati. Does anybody have any announcements to make? If there's nothing, then we can go ahead and get started. Today's topic will be transferring deep learning knowledge for scaling up hydrographic feature extraction. We'll have two presenters today for this topic. We'll have Larry Stanislavski. Larry is a research cartographer with the Center of Excellence for Geospatial Information Science in the USGS National Geospatial Technical Operations Center, or NGTOC. We'll also have Larry's co-author, Nadapan Jarankai. Nadapan is a PhD student in the Department of Geography and Geographic Information Science at the University of Illinois, Urbana-Champaign. Hi, Larry and Nadapan. Thank you for being here today and joining the call. And please feel free to share your slides and take it away.
Thank you, Alex. Hello, everyone. I'm Larry Stanislavski, working with the CGIS group. We've been collaborating with researchers from several universities to test deep learning with the UNet model to extract hydrography from IfSAR radar data in Alaska. So I'm going to review some of that progress today. Our motivation is that we're working to improve our hydrographic database, which is included on topographic maps and used for hydrologic studies. The 3D national topography model calls for the hydrography that's integrated with our high resolution elevation databases and to make the data more useful. The high resolution elevation data includes 5-meter resolution IfSAR data in Alaska and 1-meter resolution elevation models derived from lidar data in other parts of the United States. We're deriving the hydrography from the elevation data to integrate the two data sets, and this is a big task. We expect to extract nearly 300 million features from the high-res elevation data, which is about 10 times the number of features in the current hydrography database. So deep learning, we expect it's going to help us to meet this challenge. We've been testing the deep learning models to extract hydrography from various layers derived from high resolution elevation data. Working in Alaska, we've determined that using about 15 to 25% of the study area for training is sufficient based upon this 50 Hub 12 study area that I'm showing you in red right over here in the center. Can you see my mouse? The area, this 50 Hub 12 study area covers about 4,600 square kilometers. The 50 Hub 12s range in size from over about 30 to over 200 square kilometers, and the elevation down in this Potomac River Valley area is about 32 meters above sea level, ranging to nearly 1,900 meters above sea level in these mountains. Our best model currently uses 12 of these Hub 12 study area, Hub 12 watersheds to train as training of the 50, and so the 38 are test watersheds. The 12 training watersheds are shown in the tan color, and then I'm going to focus on an area to show you some of the results in this black box. The best model provides us with F1 scores that average for the 38 test watersheds of 80%, which is when we filter out likely problem areas in the reference data. When we don't filter it, those average F1 scores are about 73%. So the histogram of the F1 scores, the massed F1 scores ranges from 67%. The reference data that we're using was compiled by USGS contractors from the IfSAR data. I'm showing you the reference data. It's compiled using flow routing techniques and other proprietary techniques. And then they used they manually edited the data to fit high resolution image data. And so that's, we do have for all the study areas, we do have this similar types of contractor derived hydrography that was developed through the elevation derived hydrography program. So that's available in all these areas that I'm going to talk about. But the hope is that we can use this type of a method to kind of update that if there's problem areas, or to maybe update the data sets later on when things change. So this is the way this works is we have to derive a bunch of input layers from the elevation data that we have, that's digital surface model, orthorectified intensity, the digital terrain model, and then we derive channel depth, positive openness, negative openness, all these other input layers. This list of the 10 layers I'm showing you in this table on the bottom here is the best set of input layers that we've come up with that work best for the model that we've so far. And so what we do is we generate all these input layers for each of the Hub 12s, and they're all integrated. They're horizontally integrated on the same reference and grid system at 5-meter resolution. And then we start sampling those all for each of the training watersheds. We'll sample using 128 by 128 pixel window samples of rasterized reference data and all of those input layers. And we'll sample up to, in our best model, we're sampling 3,600 window samples for each of the Hub 12s that we're using for training. So that's with 12 of those, we have over 40,000 training samples in our best model. Then we take those and we push them through this UNet model to train that model to predict the hydrography from those. I've identified the architecture is up in the left there, identifying the encoder and decoder and classifier sections that have, there's thousands of parameters associated that get solved for when you train the model. And so when you transfer the model to other areas, you can freeze different portions of the parameters. And so these are, you can freeze encoder, classifier, all of those sections when we try to refine the model. So by freezing them, that means we're not adjusting those parameters. So then anyway, this is from our best model. On the left-hand side, I'm showing you the reference data. It's compiled by the USGS contractors, and then the predictions are shown on the right side. So you can see that the water bodies are well predicted, and we've got a lot of good network features. But we do predict more water bodies, smaller water bodies, because the reference is only generating the level, the 1 to 24,000 scale level of detail. So we get some additional smaller water bodies. We also extract the D-infinity flow lines from the elevation data, and we constrain those to follow our predictions. And so you can see this is all of those D-infinity lines. We have a method to show you thin those out of it, but we can see that it creates a well-connected network that follows similar pathways as what's in the reference. But we do have a lot, the headwater features are a bit over identified in these predictions. And so how do we thin back those headwater features? So if we take our D-infinity lines, I'm showing you on the right-hand side, and we identify what percentage of those D-infinity segments are covered by the predictions. And so we overlay those two and we calculate that. And so I'm showing you the darker blue lines are the ones that are 70 to 90%, or 70 to 100% covered by the predictions, whereas the red and the lighter lines are not so well covered by the predictions. And so we can use, maybe if we look at, we include all of the non-headwater features in. Sorry. And then any additional headwater features that are predicted at say 75% or more, then that could be a way that we can include some of those headwaters and create a good connected network from the predictions. So now, how do we transfer? How well does this model transfer to other areas? Here's our base model here. We're transferring it to all these six other Huck 8 areas that we're transferring to. There's about 700 Huck 12 watersheds included that we're testing here. We do have reference hydrography for these areas as well. And so two ways that we're transferring it, we just apply that model directly and see how well those things that we can predict for each of those Huck 12s, all hydrography there. And then we do refine the model by using a small amount of additional training. So looking at from top to bottom, left to right, from across this way, then this is the way I have these arranged, and then 1, 302. So I have them ordered that way. So we are using 3 of the 190 Huck 12 watersheds that are included in the 906 and 301 to refine the base model to that target area, and then 6 of 147 for this 906 and 302 target area, and so on. So it's a small amount of additional training to refine that model, and it takes less time because we're starting with the set of base model parameters, and then we're just adjusting those rather than starting from scratch. So it takes a lot less time and a lot less reference data to just refine the model. We don't have to do as many trials. And so this is what the results look like for those 6 Huck 12 watersheds. Blank ones, either we weren't able to generate the layers automatically, or we were using them for reference training. So you can see the distribution of the F1 scores. The darker blues are the better solutions in this area. Oops. And then down here is that 1902. So I'm showing you the minimum, the mean, and the maximum for the base when we just applied the base model directly up here. And so this column would be for this 1906 and 301. And this is when we refined it. So this is base model applied directly, and then the minimum, mean, and maximum F1 scores for the Huck 12s in each of these Huck 8s. The refined scores are down here, summarized. So what are we looking at? So these northern ones, we're going to average F1 scores of 59, and when we refined them, it moved up about 10%. And you can see that the minimum ones are the ones kind of jumped up more. And then these 3 at the same latitude as the base model, they started from 47 on up to 68, and then when we refined them, they moved on up to 72 to 77%, which is pretty good. Again, the minimums are jumping up quite a bit to me. But then over here on this southwest, this one in the southeast, it's about over 600 kilometers away from the base model. It didn't work out so well. And then we weren't able to refine it by using 2 additional Huck 12s for training. So we can see that there's, these northern ones are not predicting as well as these ones at the same latitude as the base model. And so there's possibly something different going on here. And so looking at the terrain conditions, we can see, there's quite a bit of difference in this north slope area compared to here and just at the terrain. And then, in comparison to here, this looks more like what's in this base model area, at least the terrain. But then I got from Neil Pasick, he provided me with a permafrost layer that's generated from Landsat data and several other input data layers. They're estimating the probability of permafrost in the near surface. And so you can see the darker areas up here that are affecting these northern watersheds, whereas there's not as much permafrost in these southern target areas. And then we also are looking at the vegetation, in places where there's permafrost, there's not as much tree canopy height. This data was collected by using a lidar lidar measuring device that's on board the International Space Station, along with some Landsat data. So they get some estimates of forest canopy height in here. So we can see that there's some substantial differences between the northern and the rest of the other target areas anyway. So this is so focusing in on this one area, I'm going to show you some results for that area. So pretty good predictions there. So how do we extract? We applied that method to the infinity flow lines that we extracted from the elevation, and we constrained them to follow our predictions. And then we overlaid the predictions on top, and I determined how much each of those segments is covered by the predictions. And this is the results for 200 or so watersheds. So for the headwater features, we can see the result shows that 37% by length of the headwater features are covered by 70% of the watersheds. Whereas on the non-headwater features, there's 73% of those features by length are covered by 70% or more of the predictions. That's kind of what we're looking at here. So we've got reference on this section here on the left-hand side, and I'm showing you predictions here on the right, where we are showing you only the non-headwater features from the D-infinity lines, along with the headwater features that are covered by 75% or more of the predictions. And you can see everything looks fairly similar. Water bodies are well predicted, but over in some of these areas, we're under selecting the headwater features, or underrepresenting the headwater features in comparison to the reference here down in this floodplainy area. So I'm going to focus in a little more on that area. So here is the reference, and then this is our D-infinity lines that are constrained to follow our predictions. I'm showing in black all of those ones that are less than 75% covered by the predictions. And so you can see there's not a whole lot of predictions in those areas. So in comparison, I'm showing you the geomorphic indicators up here. Number one means that there's 4 layers that go into the geomorphic layers going into this index. If all 4 of them indicate that there's likely to be water forming at that area, then it'll have a 4. Whereas if only one of them indicates that it'll have a 1. So in the places where the geomorphic indicator indicates that there's highly likely where it's number of 2s, 3s, and 4s, we can see that our predictions and our headwater features that are 75% or more covered are following those lines quite well. Whereas in the less likely places, in these headwater places where the GMI is indicating there's features in these tan colors, we have some of those features, but we're not representing them. So I'm just overlaying, for example. So how much of these headwater features should we use 75% as the initial estimate? We could go down to 60% or 50% or more. Anyway, in comparison, particularly in the headwaters, we are not as consistent with the reference as we are in other areas, other portions. So in summary, our UNet predictions of hydrography in Alaska using layers derived from 5-meter resolution IfSAR provides prediction accuracy of about 80% for our base model area. And when we apply that base model to predict hydrography target areas, it produces average F1 scores between 47 to 68%. And then when we refine those base models to each of the target areas using about a small amount, 2 to 8% of the target area for additional training, that's improving our average F1 scores to 68 to 77%, which is a more than 10% improvement. And those results are reasonably good. But except for that one place where that one target watershed 1908-03-02 is more than 600 kilometers from the base model. And that model, that it only provides average F1 scores of 50%, and that we couldn't refine it at all with additional training. So overall, the transfer learning substantially reduces the model processing time, and the training data requirements. This happens because during the transfer learning, we only need to adjust the model parameters to the target area rather than predicting all the parameters from scratch, which requires a number of trials. So for those d-infinity flow lines that we constrain to follow the UNet predictions, when we include all the non-hydrowater lines and the likely d-infinity border lines, those that are 75% or more predicted, that produces a well-connected network. So we can predict a good network from this method, but we do need to do some further testing to validate and refine that process. So for future work, we're going to be further testing the transfer learning on other areas. We're going to test using the UNet using H12 training watersheds that are distributed over a wide region that has various terrain conditions that include, and we will include soil and vegetation layers such as the canopy height and permafrost. And we've already started piling those data sets together. And then we're looking at testing a k-means clustering of all those input layers to help assist in selecting a distributed set of training watersheds that is distributed amongst all the different variables, all the different clusterings of those input layers. So, and then also we're going to implement an automated comparison method to compare the hydro predictions with those GMI layers. See if we can improve the selection of which d-infinity lines to select. And then also we'll compare with the GMIs with the reference hydrography, because in some areas the reference hydrography is better than others, and sometimes the IfSAR data is not as good. So hopefully we could try and identify some of those problem areas, and then we don't have to focus on choosing those for training as well. Or we can at least identify where the problem is.
Hello, everyone. So I am Natapon Chai, a PhD student working with Dr. Xiaowen Wang at University of Illinois at Urbana-Champaign. Today, I will be presenting in the topic of transfer learning with convolutional neural networks for hydrological streamline delineation. So let's get started. For the background, as we know, freshwater is one of the irreplaceable strategic resources for human survival and social development. Only a small amount of the freshwater is accessible, such as rivers, swamp, creek, lakes. Therefore, reliable information about the spatial distribution of the open surface water is critically important. And the NHD is the most comprehensive hydrography dataset for the United States that is managed by the USGS and partner organizations. It provides a common reference for regulations, research, and modeling. However, creating the dataset is at the fine scale from high-resolution DEM data using the traditional flow accumulation method is costly and laborious process. So the traditional flow accumulation is used to derive streamline network from the DEM. However, there are some problems with this method. Firstly, it's required threshold to extract accurate density of the drainage lines. Secondly, the result must be manually validated and edited with the high resolution image data or view data. And lastly, the flow accumulation could be obstructed by the intersection between the road or bridges and the valley. This leads to the inaccurate drainage line extraction. There are studies that to overcome these problems, and one of the most recently gained popularity is the machine learning approach. In our recent study, we proposed a convolutional neural network, CNN, called attention unit model. This attention unit model is trained on the sample from the topological feature derived from the lidar data. The results show promising streamline network extraction with the F1 score over 80%. Even though it shows promising result, the method has several problems. Firstly, the model performance is significantly low when it is used to predict the streamline in other areas. And to achieve the desirable performance, the entire model has to be completely retrained with the sample extracted from the target area. So in this study, we examined the transfer learning method to help overcome the problem of the machine learning approach. So why transfer learning, you may ask? The transfer learning is one of the techniques in machine learning that use the knowledge gained from one problem to solve different but related problems. As you can see in the diagram here, the traditional machine learning on the left, each task has separate dataset and training processes. Therefore, the knowledge gained from one task will not be retained among the models. However, with the transfer learning, the knowledge from the previous model, such as weight, features, and parameters, can be transferred to the new models. Therefore, the new model required less training time and smaller data set for training. In this study, we aim for 3 goals. Firstly, we test whether the general purpose CNN can achieve better performance than the recently proposed attention unit model. Secondly, we compare the transferability between the model trained on specific task and the model trained on the large general image dataset. And finally, we examine the potential of scaling up the automated streamline delineation process to the larger areas. We use the data from Rowan County area in North Carolina and the Covington River in Virginia. When we examine the 2 study area, we found that there are several differences that may impact the performance of the CNN when applied the model on the different location. First, we see that the Covington area is about 6 times larger than Rowan County area. Secondly, the Covington area has almost 4 times larger elevation variation, and these 2 locations are about 250 miles apart. To examine the differences further, we randomly select the stream and non-stream pixel in both locations and examine the t-distributed stochastic neighbor embedding, or TSNE plot, and the principal component analysis, or PCA plot, of the pixel values. As we can see here, the plots show clear separation between Rowan County and the Covington area, especially in the PCA plot. In the TSNE plot, not only the data between the 2 areas are clearly separated, but also the distribution of the stream and non-stream pixels are clearly different. Covington area are more spread out, which means more variation in the stream and non-stream pixels. For the data preparation, first, all raster layers are normalized to the range of 0 to 255. Then we divided the study area into top and bottom half. 200 sample patches of the size 224 by 224 are extracted from the top part, then augmented to create a 1,400 sample patches. We use these 1,400 patches for training. Another 30 patches are extracted without overlap with the first 200 patches. These patches are used for validation. The test dataset is generated using the entire bottom half of the with the moving window method to eliminate the edge effects. This is the example of the one patch of the input dataset in Covington area. Now, let's look at the result. In the first experiment, we compare the performance of the UNet model with the ImageNet backbones with the attention unit model. Note that all the model except the attention unit model are fine-tuned with the same hyperparameters as shown on the left-hand side here. For the attention unit model, it is trained from scratch with the same max epoch and batch size, but we use the reported learning rate from the previous study as shown on the right-hand side. The earlier stopping and the model checkpoints callbacks are used to monitor the validation lost, stop the training when no change in lost, and to save the model with the highest validation accuracy. First, we look at the third column. We find that the best performance of the ImageNet backbones with randomized weight can achieve the performance as high as attention unit model. The highest is DenseNet 121, which is 0.5% higher than the attention unit model. Then we compare the third column with the second column, which is the performance when we initialize the model with ImageNet pre-trained weights. We find that the performance of all models are significantly improved, as much as 6.97% by inception ResNet v2. When we compare all the performance, we find that even though the attention unit model is trained from scratch, its performance is significantly lower than DenseNet and ResNet models initialized with ImageNet pre-trained weights. The biggest improvement is the DenseNet 165, which is improved by about 4% from the attention unit model. Moreover, when we look at the parameters numbers, we find that the top three models has significantly less parameter than the attention unit model. The result in this table also confirm that the performance improvement are mainly contributed by the ImageNet pre-trained weights rather than the differences in the model architecture. For the next experiment, we selected the DenseNet 165, ResNet 50, and DenseNet 121, and attention unit model as the highlighted here, to test the transferability of the ImageNet model. Next, to establish the baseline performance of each model in the Covington area, we fine-tune the selected ImageNet model and train the attention unit model from scratch using the Covington dataset. These results are the baseline performance because they only have the knowledge from the Covington area. In the second column, we can see that all the three ImageNet pre-trained models outperform the attention unit model. Additionally, we can observe that even though the model are fine-tuned or trained from scratch using the Covington area dataset, the performance significantly decreased about 30% on average compared to the performance of the model in Rowan County area. This drastically decrease in performance can be contributed by the quality of the reference data and variation in data distribution as we shown in the PCA and the plot earlier. The last experiment, we examined the transferability of the models. We fine-tuned all 4 models from Rowan County area using Covington area dataset and evaluate them on the Covington area test dataset. There are improvements for all models when we compare between the performance of the training on the Covington dataset directly on the third column and the fine-tuning model from Rowan County dataset to Covington dataset in the second column. The model were improved as much as 3.99% and achieved the highest F1 score at 65.58% by ResNet 50. It is also worth to mention that the parameter of the ImageNet model are significantly smaller as compared to the attention unit model. Additionally, the training time and the number of epochs until convergence of the ImageNet model are significantly better than the attention unit model. Then we compare the performance of the transfer model with the traditional machine learning method, which are random forest, support vector machine, and gradient boost classifier. Compare all the methods, the ResNet model show exceptional performance. Other deep learning methods like DenseNet 169 and 121 also perform well, highlight the benefit of the transfer learning and the fine-tune strategy. However, the attention unit model lag behind and can only achieve the F1 score of 48.95%. Traditional methods show limited effectiveness in the streamline delineation task. So, in conclusion, the result from the Rowan County shows significant higher performance can be achieved with the transfer learning. As we can see that DenseNet and ResNet models initialized with ImageNet pre-trained weights outperform the attention unit model. Secondly, the result from the Covington area show transfer learning can significantly improve the model performance as high as 3.99% in the ResNet 50. And we can see that the top 3 ImageNet model outperform the attention unit model in the Covington area. The knowledge gained from one area can help to improve the performance of the target area also. And lastly, the result from the Covington area also show the scalability benefit of the transfer learning, as the model pre-trained on the ImageNet are significantly smaller. DenseNet 169 has 2.7 times, and ResNet 50 has 1.6 times less parameter than the attention unit model, which could help to scale up the model more efficiently. And the time per epoch and the number of epoch to convergence of the ImageNet model are significantly shorter than the attention unit model, as the ImageNet takes about 50 epoch and the attention unit model take about 120 epochs to convergence. For the future work, we are working on testing the transfer learning model in Alaska area. And we are also looking into other techniques of transfer learning, such as domain adaptation and meta-learning techniques, to address the geospatial differences such as the resolution and variation of elevation. I also created a Jupyter notebook to help teaching the transfer learning tutorial. You can access this here in the link.
Thank you very much. The hydrography community calls are generally held on the 4th Tuesday of the month. However, we will combine the calls for November and December to avoid the holidays. So the next call will be held at the end of November or in early December with the date to be announced. Drew will send out a notice and calendar invites for that call soon. Please stay tuned for that link and a link to the recording in the coming days. And thank you very much.